All right, I will begin. Ahem, ahem, ahem. Dear Heavenly Father, we thank you for the day. I thank you for the quiz being over for you guys. Now for the grading to begin, pray that you give me grace and mercy and understanding, much understanding. Thank you for this class. Just pray that you help us to understand a little bit more just about your creation today, Lord, as we study it together. In your name we pray, Lord Jesus. Amen. Golly, look at this. Yes, I mean, mercy on my eyes. Look at this. Golly, what have I done? Yeah, it's all my fault. I should have listened to Cooper. What's that? Yeah, I think I'm going to grade these. Yeah. All right, so projections and orthogonal decompositions. For a real inner product space is what we're going to be talking about today. If I play my cards right, we will find our way to least squares by the end of class. Now, so I guess first things first, I will remind you what we're dealing with here is a inner product space, right? We're considering what? We consider vector space V over the reals, right? Paired with what? Paired with inner product. We use brackets like this. This is a mapping, of course, from V cross V back to the reals. And what are its properties? Symmetric, right? Symmetric, it's bilinear, and it's positive definite. Right? Another thing we'll be working with today, we'll assume that V is also a normed linear space. Normed linear space, or NLS, where the norm of x is just equal to the square root of the inner product of x with x. So that's our setup. We're using norms which are induced, which is induced from the inner product, and this is our context. Now, there is of course a larger discussion to be had here. Is it the case you can always, well, yeah, we can always induce a norm from an inner product. You might wonder, can you go the other way? That's actually an interesting question, and the answer is sometimes, but not always. But anyway, I have a rather insidious homework problem in my advanced calculus class, which investigates that. But I'll leave that for there. All right, so let's see, a theorem. Let's start out with an easy theorem. W intersect W perp is 0. Have I proved this already? I don't remember if I have or not. I don't think I have. So let W be a subspace. Anyway, I'll prove it again if I haven't already. Let W be a subspace of a vector space. Again, V is still going to be an inner product space, right? Let W be a subspace, and let W perp be the perp of W. Then their intersection is 0. All right, so let's see how this goes. Now, I guess some of you are wondering what's W perp. If you forgot, W perp is by definition what? V and V such that what? The perp to W is the set of vectors in V which are orthogonal to every vector in W. Geometrically, it's the perpendicular space. Okay, fine. So let X be an element of W intersect W perp, right? Then what? X is an element of W, and X is an element of W perp, right? What's that tell you? Why?
Because the only element that an element of both is 0.
That's just saying what I'm trying to claim again. But why? Why is it 0? What does this tell you? If it's in W and W perp, right? Well, of course, if x is in W, it's in V, right? So this is a vector in V, but it's also a vector in W perp, right? Which means that by this condition up here, x with x has to be what? 0. Now we get what you said, because the only way we can have an inner product of a vector with itself be 0 is if it's the 0 vector. That's positive definite, part of being positive definite, right? What does this prove? Therefore, W intersect W perp is a subset of what? The set containing 0, right? But in fact, I mean, okay, I can offer a second argument, or I could just be greedier and just make these double implications, and it would still be logical, right? You notice that? This argument is reversible. This is reversible, right? This, well, there I'm a little bit nervous about that one. That one could be misconstrued. Fine, I'll give a separate argument. All right, so what's the other thing? Let x be an element of the 0 set, which is a stupid way of saying what? X equals to 0, right? But W perp is a subspace of V. We proved that the other day, remember? That's the one we did prove. I may have called it S perp at the time, but we proved that if you look at the perp, it forms a subspace. I mean, you could prove that. So this is a subspace, therefore 0 is an element of W perp, right? If it's a subspace, it has 0 in it. Also, W is a subset of V, subspace of V, right? Therefore, 0 is an element of W. Therefore, 0 is an element of W intersect W perp, which tells me what? The 0 set is a subset of W intersect W perp. Put this all together, what do you got? Conclusion. W intersect W perp is just the set containing 0. Is that, well, I hope it's reasonable. I'm pretty sure it's reasonable. I don't know if you followed it or not, but I think you can follow it if you think about it for a little bit. All right, so what's our next order of business? Well, how about this? Theorem. If W is a subspace of V, an inner product space, as usual, then there exists something called the projection onto W, a mapping from V to W, linear transformation, and there exists a mapping called orth W, which is also a mapping from V, but this time to W perp, such that, well, I guess I shouldn't say this. I should say, I don't want to say W and W perp here. That's actually the range of these maps. I'm going to have to replace this with V so that I can make sense of what I'm about to write. Sorry about that. So to V, such that the orthogonal, such that the projection of W plus the orthogonal projection onto W is equal to the identity on V. Moreover, orth W of x inner product with the projection onto W of x is equal to 0 for all x in V. All right, so here's how to prove this. I mean, so I need to construct these operators, all right? These linear transformations, the projection and the orthogonal projection. The proof, the construction is just a simple add-on to the thing we did last class, right? So like last class we learned that, so here's the proof. If, let's say, beta is a basis for W, let me say beta tilde, then beta equals to V1, V2, dot, 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 Vk is an orthonormal basis for W. Right? Obtained by how? The Gram-Schmidt algorithm, right? You can obtain it by the Gram-Schmidt algorithm. So we can construct an orthonormal basis for W, right? Now W is a subspace. What can you do to any basis for a subspace of a vector space? What could you do? We can extend it to a basis for all of V, right? So extend beta to gamma tilde a basis for V. Right? Now, we can do that by our previous basis extension theorems earlier in the course, right? We just adjoin vectors outside the span. And we can keep doing this, but we can't do it forever because we're assuming V is a finite dimensional vector space from the outset. I should probably have told you that. Sorry about that. Finite dimensional. All right. So now, this gamma tilde, it's not necessarily going to be an orthonormal basis, right? We didn't get that from our earlier theory, but what can we do then? Just you run gamma tilde through the what? The Gram-Schmidt algorithm, right? And since we put, this gamma tilde, I'm doing it. Gamma tilde is equal to beta union with say beta perp tilde. All right. And after you run the Gram-Schmidt algorithm, of course, beta stays fixed, right? What happens when you orthonormalize a set which is already orthonormal? Nothing, right? Like this would be a very easy test question. Orthonormalize. Run the Gram-Schmidt algorithm on the standard basis. What do you get? With respect to the Euclidean inner product, you dot product, you just back where you started. I mean, it's stupid. So when I run Gram-Schmidt on gamma tilde, what pops out? Run the Gram-Schmidt algorithm on gamma tilde, obtain gamma, which is just going to be beta union with, say, beta perp. That will be orthonormal. All right? Now I just need to enumerate some things. So notation. We had beta equals to V1, V2, dot, 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 Vk. And for my convenience, I'll say beta perp is equal to what? I mean, I don't know. I guess I'll just say V, what, k plus 1, Vk plus 2, Vk plus what? Well, let's write it more civilized. This is Vn, right? It's a basis for V. I'm assuming the dimension of V is n, all right? All right. Check it out. Definition. Well, first of all, forget this thing. Let the projection onto the subspace W of x equal, here it is, the sum I equals 1 to k of the inner product, all right, of x with vi. Okay? And let the orthogonal projection onto W of x equal to x minus the projection onto W of x. For all x in the vector space, okay? My first question to you, are these linear transformations? I invite the reader to show that these are in fact linear transformations. You can show these are linear. It's almost immediate from their formulas, right? The argument is appearing in an inner product, and the first slot of the inner product is in fact a linear, right? It has that linear identity. So that gives us linearity. Now, is it true that the sum of these operators gives you the identity? Remember last time I talked to you about how x can be rewritten as the sum I equals 1 to n of x with vi. That's an identity for an orthonormal basis. But this gamma that we've constructed is an orthonormal basis. So I have this identity, right? And then you just take that sum, break it into two pieces, right? This equals the sum I equals 1 to k of x with vi plus the sum I equals k plus 1 to n of x with vi. You're like, wait, but hold on a second there, mister. How do you know that this is, now this is clearly the projection, right? Onto W of x. It's the shadow of x onto W, all right? How do I know that the other piece is the orthogonal projection? Just come down here and actually calculate it, right? If you look at this, come back to this, the definition of orth, you can see that this is what? This is like the sum I equals 1 to n of what? X vi minus the sum I equals k plus 1, I equals 1 to k, right? I equals 1 to k of x with vi, right? So what happens when you take the difference of these sums? You lose the first k of them, right? That's how finite sums work. And all you're left with is the end of the sum, right? From k plus 1 to n. So if you look at this, and you look at this, those are equal, right? And so this is nothing more than the orthogonal projection onto W of x. All right? And what else did I claim? I claimed that these are perpendicular, right, in the sense of the inner product. How do I prove that? If we calculate the inner product of the projection onto W with x with the orthogonal projection onto W with x, what do we get? Bad bounce. So I'll just get to it. By linearity, you pull out I equals 1 to k. You pull out a sum j equals k plus 1 to n. You got yourself inner product of x with vi, the inner product of x with vj, and then, of course, over here, vi with vj. This is what you get after. So basically, all I'm doing is plugging in the formula for the projection, plugging in the formula for the orthogonal projection. I pull out each sum, and I pull out the constants, the inner product of x with vi and x with vj. These are just numbers. They pull out of the inner product, and you're just left with this, right? But then focus here on this right here. What is this, though? I is where? I is an element of 1, 2, k, right? J is an element of k plus 1, k plus 2, somewhere in here, right? In other words, that means that vi is an element of what? W, by construction. And vj is an element of what? W perp, by construction. So that is 0 for arbitrary I and j. And there you have it. So guys, what's a corollary to this? How about this? W, direct sum W perp is what? The whole space, right? What's the proof of that? Well, first of all, we already proved earlier today that W intersect W perp is 0, right? So I know that these subspaces are independent. Now I need to show that they in fact sum to give the whole space, right? But if x is an element of V, then you can also see that the projection onto W of x is an element of what? And the orthogonal projection onto W of x is an element of what? Fill in the blank for me. Thus, x is equal to a projection onto W of x plus the orthogonal projection onto W of x, which is an element of W plus W perp. That completes the proof. Where does the projection of W land? Projection of W of x lands in what space? I wrote this to start with, but I backed off of it because I wanted to add the maps. To do so logically, I need to have the codomains matching. Look at the formula, right? Where is this? These VIs are where? These are in W, right? You're taking a linear combination of vectors in W. You're again in W. This is a W vector. So this is an element of W, and this guy is in W perp by construction. So we have in fact shown that. All right? I mean, oh, why did I just use that thing? Oh, eventually I'll remember. Another little theorem. Here's the theorem. If VW is orthogonal, all right, it's an orthogonal set of vectors, then the length of V plus W squared is equal to the length of V squared plus the length of W squared. In fact, if I had more time on my hands, I could prove this for n by induction. This easily extends to 3 or 4 or even n-fold orthogonal sets. That gives you the so-called generalized Pythagorean identity, right? Now, what's the proof of this? Here's the proof. So, to calculate the norm squared, it's easy. What we do, if this is the case, what's the norm of x squared? Right, inner product of x with x. You recognize this if you've had calculus 3. To calculate the length of a vector squared, we take the dot product of the vector with itself, right? Okay, so inner product of v with v, how's that work? V plus v with v plus w is what? By properties of inner product, by bilinearity, this gives me vv plus vw plus wv plus ww. Zero. Zero. Because those are orthogonal, right? By definition, those are 0. But also by definition, this is what? Length of v squared, right? Plus the length of w squared. And there you have it. Pythagorean identity. This applies, for example, to the orthogonal projection and projection onto a subspace, right? The orthogonal projection and projector with respect to a given orthonormal basis, what do they do for you? They give you, right, a vector which lies in the subspace and a vector which lies off the subspace, and the total length of the vector is a sum of the squares, well, it's the square root of the sums of the squares of the projection piece and the orthogonal piece. It's very nice. All right, so now I need to get back to some sort of more specific things about Rn for a little bit here. So I want to tell you, and I don't think I've done this already yet, our next, I probably should. I don't think we need that stuff over there now. Okay, so here it is. S perp is equal to the null space of the transpose of the matrix which is formed from concatenating the vectors in S. So if you have S is equal to, like, say, V1, V2, however many you like, that's a subset of, say, Rn. And this notation, S bracket, that's the matrix which is formed from gluing those vectors together, like so, to make a what? What would this be? A n by k matrix, I guess. Yeah. So the perp, all right, the perp to S, which is a subspace, right? You can calculate it simply as the null space of the transpose of that matrix. Isn't that? I mean, that to me is very, very simple. How do you prove this? It's really just a simple calculation. What does it mean for a vector to be in the perp to S? So suppose you have x as an element of S perp. What would that mean? It's perpendicular to what? All of these vectors, right? So what's that give you? That gives you, like, v1 dot x equals to 0, right? v2 dot x equals to 0, and so forth. vk dot x equals to 0, right? Gives you these k dot products. But any dot product we can write as what? A product of a column vector and a row vector, right? So I can rewrite this as v1 transpose times x equals to 0, v2 transpose times x equals to 0, and so forth and so on, vk transpose times x equals to 0. That's just changing my dot product to a matrix product, a row column product, all right? But we have these k separate equations, right? And you can just collect them into one big matrix equation using properties of matrix multiplication. You just got v1 transpose, v2 transpose, vk transpose, all times the column vector x equals to 0. But this is precisely S transpose, matrix S transpose. And so we have this equals to 0, which is, of course, to say what? X is an element of the null space of S transpose. All right? Let me show you a simple application of this. Here's an example. This example will be based, I have maybe a pair of homework problems in Mission 8, which are kind of based on this story I'm telling here right now. So here's the story. W is, say, the span. I'll keep it really simple in here. Let's say 1, 0, 0, and 1, 2, 3. It's relatively simple. So now then the question is as follows. Find an orthonormal basis for W. All right. Step number 1. And then step number 2, extend, let's call that beta. Extend beta to gamma, which is beta union some other vector, whatever, say x, an orthonormal basis for all of R3. Here's how I would do this problem. To find the orthonormal basis for W, that's not hard. All I got to do is run the basis that I'm given through the Gram-Schmidt algorithm, right? So if you run the Gram-Schmidt algorithm, basically we take this set. I'm just going to tell you what it pops out. You can run it formally if you want. Okay, so this will go to beta equal to, my first vector is just the first vector. That's already normalized, so I'll just keep that. The second vector, all I do is 1 over the square root of 13, of 14? 13. 0, 2, 3. These are orthogonal, and they're normalized. 14. 9 plus 4 is 13. But that's gone. Why would I use 1? If I had 1, the dot product would not be 0.
Oh, right, sorry.
So the Gram-Schmidt algorithm removes that part of the second vector, the part that goes in the first direction. Okay, that's orthonormal. That's the same span. That's the span is W of that set, I assure you. This is the Gram-Schmidt algorithm. I did it in my head. Now to find x, well, x will be an element of the null space of 1, 0, 0, 1, 2, 3. You see, I could use these vectors, but that would be stupid because that's got a square root of 13, which I don't like. So I already know that these two vectors, right, are a basis for W. And so anything that's in W perp should be in the null space of these transposed, which is that. So I solve that. What is that? Okay, well that's the same as what? 1, 0, 0, 0, 2, 3, right? And so if I have that times x1, x2, x3 equals to 0, what do I have? I've got x1 equals to 0. I've got 2x2 plus 3x3 equals to 0. Lo and behold, my x is equal to 0. Let's say x2 is equal to, I don't know, 3. If x2 is equal to 3, then what's x3 equal to? There. As you see, I have managed to satisfy my fear of fractions. We've avoided them. Okay, so there you go. That vector is not yet normalized, though, right? So the x, let me call the x that I want to join there. Let me call this x tilde since it's not the one I want yet. Fine. X is 1 over the square root of 14, 0, 3, minus 2, and there you have it. You add that, you join that to those two vectors, and you got an orthonormal basis for R3. And if you were paying attention, you should be grateful that I've shown you this, because this means that you didn't have to randomly pick something outside of W and then run Gram-Schmidt a third time. Because the second application of Gram-Schmidt, the one where you subtract two dot products, is a drag. This is way easier. So some kind of interplay between this null space calculation and just full-bore Gram-Schmidt is like an optimal way of approaching these kinds of low-dimensional problems, I think. All right. So getting back then to the problem I advertised before, we're about to solve. Yes, sir? I'm sorry, ma'am.
Where did square root of 14 come from?
Normalize. So the length, what did I do? I mean, this is the length of this is 9 plus 4 square rooted, which is 9 plus 4 is, oh, that's 13. What, Lorenzo? I blame you.
Last time I was wrong, so I wasn't. Yeah, she made me ask.
She's, yeah, but you put this 14 in my head. It's all your fault. Wait a minute, no, I blame Danica. Okay. All right, there we go. Okay, guys, so we solved all kinds of equations early on in this course. Remember that precious time where we actually solved equations with numbers in them? I know it was only a day, but there was that day, right? That precious day where we did high school algebra, and it was good. Oh, okay. So, if you think about this, though,
That was quite complex. That was almost calculus.
if we have this equation, ax equals to b, right? And I mean, I guess a doesn't even have to be square, honestly. I think this derivation makes sense even if a isn't square. But if this is inconsistent what? What's that mean? That means that B is not an element, right? I wrote B as an element of the column space of A for shame when I was talking about this the other day. I said not an element, but I don't think I put the thing through the not. I was watching the video later. I noticed that. That was unfortunate because I shouldn't do that. Now, so here's the thing. Suppose you want to make this as close to, no, it's not consistent, right? So that you can't make this equal to 0. But what you could try to do is try to make the norm of ax minus b as small as possible, right? So if you think about this, you could take this vector, right? And you could feed it into the, you could look at, like think of column space of A as your W, all right? And look at shadows of this onto W. So if I can draw a picture for just a second here. Here's the column space of A. B is off up here somewhere. Here's the origin, right? And so you can break this up into two pieces, right? There's this piece, which is the projection onto the column space of A of B, right? And then this over here is the orthogonal projection onto the column space of A of B. Those two things added together give you B. And they're perpendicular. So this, right, is going to actually be equal to what? It's equal to the length of the, what? The projection onto the column space of A of ax minus b, right? Squared, plus the length onto the orthogonal projection onto the column space of A of ax minus b squared. Now you're stuck with the second term. There's nothing you can do about this. This is basically, the bigger that is, the further you are away from the truth. And there's nothing you can do to fix it. If B is not in the column space of A, it's not in the column space of A. It's not a solution, it's not a solution. Like, you're stuck with that, right? But this you could make smaller, right? What's the smallest you could make this? If you can make this 0, right, that would make this as small as possible. So what I'm trying to say is the point in the column space of A, which is closest to B, basically, is this point. There's no way to look at this. This point right here is the point which is closest to B in the column space of A. Let's see here. Now, if that's 0, what's that mean? Let's see here. If we could solve, basically, if we could solve, oh man, I got lost all the way, son. Lost along the way here somewhere. So here's the theorem. Oh, let me just, I need to get the projector out anyway. Let me just do it now. So what I'm about to derive for you are the so-called normal equations. The normal equations say basically this. If you want to find the next best thing to a solution, the thing which is most closely, the closest thing to a solution that you have, in the case that the system is inconsistent, you can solve the so-called normal equations. These, well, anyway, I'm working on it here. Let me derive them for you. Oh, come on. We'll eventually figure this out. So my first point is simply what I was trying to just tell you, is that if AX equals to B is inconsistent, then the solution of AU equals to the projection. So if I can find A times U and get that equal to the projection onto the column, why is it possible to solve this equation, folks? You're like, you just got done telling me that AX B equals B is not solvable. I'm kind of worried this matrix A is degenerate and I can't solve things, right? Well, that's not this right here is made to order, like the projection onto the column space of A. This, whatever B is, who cares? This is in the column space of A by construction, right? That's how the projector works. We make it projects into the column space of A. So that means by construction you can solve this. You can find a U. And whatever U you find there, that right here makes this 0, right? That makes this 0. And so that's as small as it can be. Okay, so that's point number 1. Now, how do you actually do that, though, right? Like, you're like, okay, so what you're telling me is if I want to find the best solution to an inconsistent system, all I got to do is pick a basis for the column space, like we called beta, right? Well, first of all, I pick a basis. It's called beta tilde. I run Gram-Schmidt on that, make it orthonormal, right? Then I pick other vectors outside of the column space, and then I run Gram-Schmidt on it again in order to obtain an orthonormal basis for the whole space, right? And then I just construct the projection operators and solve the system. That's not so bad. No, that sounds pretty awful, actually. That sounds like really, really kind of awful. Because Gram-Schmidt is really like it's not the easiest thing to do, right? Well, that's why this next theorem is so precious. If AX equals to B is inconsistent, the solutions of this, in fact, are just solutions of the normal equations. So to find the vector which produces the projection onto the column space, you just solve this corresponding system, A transpose AU equals A transpose B. And the reason for that is just this system of equivalences here. If this is equal to that, that means that if you subtract this and that from B, you get B minus AU is equal to B minus that, right? Now this is by construction the orthogonal complement, orthogonal projection onto the column space, right? Like the proof we did earlier today. B minus AU then is what? It's in this, the orthogonal, though that's in the column space of A perp, right? Column space of A perp is the null space of A transpose. All right? So B minus AU is in the null space of A transpose, which is to say that A transpose times this is equal to 0, which is to say that A transpose AU is equal to A transpose B. Normal equations, no Gram-Schmidt, just a plain old garden variety system to solve. Not the system you're given originally, but a related system. And this is where least squares regression comes into play. This is actually least squares regression, the formulas I'm about to show you here. Now, of course, details, if you have the determinant of A transpose A is non-zero, then there's a unique solution. If A transpose times A wasn't, if the determinant wasn't 0, then you could have infinitely many solutions to the least squares problems. Hey, but you still got solutions, so what's the problem? So here it is. Here's the linear least squares problem. Find values C1 and C2 such that this line most closely models a given data set, x1, y1, x2, y2, dot, 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 xk, yk. Perhaps you saw this in, like, I don't know, statistics, perhaps? I don't know. Probably doesn't look like this, though, right? You're given, like, a data, you're given, like, a model, and then you're given a data set. You're supposed to, like, choose parameters for the model that make the data most closely relate. I'm not sure how they pitch. I never taught statistics. I don't know how it looks in there. But I do know that this is the same math. So here's what that looks like. You're trying to solve this overdetermined system of equations, right? This gives you this system, and you're trying to solve that. But that's, you know, if these points don't actually lie on the same line, then this is an inconsistent system. Here, an actual example with numbers. Check it out. 0, 2, 1, 1, 2, 4, 3, 3. The model is just a line. We plug it in and plug it in. And so this is the system I'm trying to solve, you know. And so I multiply by M transpose, and that gives me this little 2 by 2 matrix. And I multiply the inhomogeneous term by M transpose, I get that little 2 by 1 matrix. And so I have to solve, but it's a 2 by 2 system, right? So I can solve by inverse, and there you go, 3/5, 8/5. Basically, y is equal to 3/5 plus 8/5 x is the line which most closely goes through these 4 points. It minimizes the distance from the line to that data. That's the best fit line. That's the thing we do in physics with the graphing and the awfulness. And if you had a bunch of points in R3, like endpoints, and you could ask what's the plane which is closest to this point by minimizing the, you know, basically trying to find C1, C2, and C3, which are as, you know, close as you can to get all these points. That gives you a corresponding system of linear equations. You find the normal equations. And like, here's an example. Here's 1, 2, 3, 4, 5 points. Those are not on a plane, but you work out the normal equations, and you can find the plane which is closest to those 5 points. In fact, it's that z equals 89 over 293x plus 32 over 93y plus 19 over 19 over 93. I decided not to give you you guys one of these this semester. You're welcome. Yes, here. Oh, I saw some of you were like, oh man, I want to do this. You can also look at nonlinear least squares. Like if you've got a nonlinear model, you may be able to like linearize it and still do least squares. For example, if you have an exponential model, you could run it through the logarithm, something like that. Sometimes you have a nonlinear model, but the coefficients appear linearly, like this quadratic, and you can still do least squares. As long as the coefficients in the model appear linearly, when you try to fit the data, it gives you linear equations, which are generally inconsistent, and then you can do least squares. So I have an example of that. We've talked about inner products already, so that will bring us to my last topic for today. Yeah, we're good. So, but you guys are talking, that means I get an extra minute. So, so you can consider the space of continuous functions from minus pi to pi with inner product, as we talked about, integral from minus pi to pi of f of x g of x. And you can show that the set of sine and cosine functions is an orthogonal set. Because if you calculate the integrals of like cosine, cosine, or sine, sine, or sine, cosine, you get 0. Unless they match, in which case you get pi. So that means that these all have length square root of pi. The length of sine or cosine in this world is square root of pi. And so if you normalize, you got this set of orthonormal. This is an orthonormal set of trigonometric functions. All right? So what you can do is you can study the projection of functions with this set, right? So like, for example, you could look at the function minus 1, 1. So this is like it's step function, right? And you could look at the projection of this function onto the trigonometric set, right? And now, admittedly, it's an infinite series, so I'm glossing over something considerably insidious and malevolent that we won't cover, convergence. But there it is. You can calculate the projections, and these are just like little integrals you got to do, like integrate with respect to cosine or sine. But it's the number 1 or minus 1. They're not too bad. You do the integrals, right? And you figure out what the coefficients are in the projection. Just the basis is infinite now. And after a little bit, you work out the components. They end up being 0 and 4 over k for the sines, and it's 4 for the initial sign. I believe the cosines all work out to 0. And that gives you this unending sum of sine functions. This is a Fourier series. 4 over pi sine t plus 1/3 sine 3t, so forth and so on. This is a trigonometric representation of that step function. The graph of this is this. And this is what MP3s do. Like MP3s take music waves, basically, right? And they take them, rip them apart into their Fourier components, encode that data, and compress it and junk. And that's how you guys listen to music with 1s and 0s. Because we rip it apart into frequencies, and that's the Fourier decomposition. And here's a picture of the first few Fourier. This little jump at the edge is called Gibbs phenomena. It usually jumps about 10%. You can't get rid of that. Well, there are various algorithms for getting rid of that, but it's an essential feature of the Fourier transform. Anyway, there you go.